Okay, good morning, everybody. This is our first lecture. So today I will combine our last theorem with some new ingredients. So first I will tell you about a very nice formula. So look at an irreducible Markov process. It's just one. On a finite state space. Yeah, with, let me call the generator, the Markov generator L. And unique stationary distribution mu. Good. So I will consider the L2 inner product with respect to this stationary distribution. Okay? So here I don't have a sequence, just one Markov process, one generator, and okay. And so I will define a number associated to two subsets of my state space. First, a function, I will define, given two disjoint non-empty subsets of your state space E, let me define a potential as a function defined on the state space, which is the unique solution of the following problem. So first, we define the green. We define this function as equal to 1 over the subset A. So we put a 1 here. This function will be 0 on the other subset B. And then on the remaining points of E, you will complete this function harmonically. Okay? Good. Now I will define the capacity between these two subsets, these joint subsets, as you take the inner product, L2 inner product, with respect to the invariant measure of L applied to this potential. Yeah. Comma. This other potential. Okay. This is what we define as our capacity. Okay, and so far I'm not assuming any reversibility. Okay, this is just a reducible Markov process with generator, with stationary distribution, and I can always define this guy. Here, the uniqueness is because the generator L is irreducible. This follows from irreducibility. Okay. It's very easy to see that it's true. And so you can also write this product as okay, observe that this other potential is just equal to 1 minus VIB. It's okay? It's okay? It's very easy to verify that this is a solution of the corresponding problem. And so now I can write the capacity as just this product. Okay? In the reversible case, this is the directly inner the square of the directly norm of this function VIB. Yeah? Good. Now I have the following very, very nice formula. Suppose that you are starting your process in some point X. You have a subset, a non-empty proper subset of a steady space. Let me call it A. And now you integrate. Sorry. And you have here a real valued function defined on the whole state space. And suppose that you are interested in computing this integral. So let me put here the heating time of the set A. Here you are starting at the position X, and so you start here. You look at your Markov process, and someday you will reach the subset A for the first time, and then you are here integrating on this time interval. Yep, and you compute. Let me compute this expectation. This is the kind of expression that we had in our last theorem yesterday. Yep. Okay, that is actually equal. It's not an estimate, it's not an approximation, it's actually equal to. In my denominator, I will use this capacity. Here, I will need to compute the capacity between the point X and the point A. Okay. I can also write a formula in which you are not starting at just one point. You are starting in a subset, but then you will need to say what the starting measure is over A, and if you use the harmonic measure over A, so you get another formula with the capacity between the starting subset here. Yeah? But okay, we are starting at some point X. This expectation will be exactly equal to, you use capacity here in the denominator, and here now, this is just the inner product with the L2 inner product with respect to the invariant measure of, here you put your function G, and here the guy is the potential. Let me see the potential X. Yes, X A. Sorry, we'll write bigger. The exponential x a. Just with one remark that this is not exactly true. Here you need to compute the solution of this problem, but with the adjoint of this generator L with respect to the invariant measure mu. I mean, it's not with respect to the original process. It's respect to the, how do you say, the joint of this original process. Okay. Anyway, I will not use exactly this equality. It will be enough to me an estimate. So here we can estimate this the absolute value of this expectation with this expression. Anyway, this will be a function between 0 and 1. So here I can change g by the absolute value of g. And so here is bounded by 1. And here just compute the integral of g with respect to mu. I will use this bound, this very nice bound, now with I will combine this bound with our last theorem. Okay, now let me come back to the metastability problem. So let me just draw one well and another well. So remember that my function Qn put an X here. My function Qn was a function in which you observe all these rates at which you can escaping from I to j, and you sum all these rates, yeah? And then we would like to show that each of my subsets EI are wells, are really wells. And then first we define these numbers associated to these functions. These numbers Qij, this number Qij is just the expectation of this number of this function with respect to the invariant measure condition to this well. It's just that. Okay, we define these numbers. Then, in our theorem, in order to prove that we are actually escaping in exponential time, we are in the limit, we see a Markov process jumping in an exponential time from the well EI. We need to prove that these numbers, the sequence of numbers converges. Yep. Then we need to be smart to choose some points inside the wells, which we are calling the meta points, so that you are able to prove that you go uniformly on this over this subset. You go very quickly to this. You reach very quickly this meta point before jumping, before escaping. Okay. Here I'm comparing this value with these numbers. But you know that these numbers are converging, so they are bounded, and I don't need. Maybe I could forget that, but anyway, I would like to write. I like to write this expression because now this expression doesn't depend on the time scale you are looking at your process. Because if you, for example, you speed up your process the velocity twice, then this is multiplied by 2, but this is divided by 2. Okay, so this is an invariant quantity with respect to the time scaling which you are looking at. Okay, just for that I wrote this Qn here multiplying this expression. But so we need to prove that actually we can bound this expectation with the expectation of this heating time, the heating time of the meta point. Yes, and we need to prove that the expecting value of this heating time to the meta point, the time you need to reach the meta point, is going to 0 uniformly on the well. This is just our first condition. Our next condition is so this is our enemy here. We need to defeat this function. This is the function that we need to change by its mean. Yep. And so what happens? For example, if you remember, in our example of the 2 cycles, we saw that this function Qn was a function equal to 0 almost everywhere, and you had just one point in which Qn was equal to n. So if this function is bounded, so this estimate is the same thing that this other estimate, yeah? But in general, this is not a bounded function. In general, you will see something like that, in which it's very difficult to escape from the well. This is the reason for which you are inside the well. And so when you escape with a very large rate, but this is a very difficult point to reach. This is the idea behind the applications of this theorem. So in general, you cannot hope that you can bound very nicely this function. So this will be the big problem, the big deal in applying this theorem. Good. This was the third condition, which is saying that you can actually defeat your function Qn. And finally, with just these conditions, you can conclude that your process Xn is going to is convergent to a Markov process, and actually these are the rates of the Markov process limit. Okay, this was our theorem yesterday. By now, these 2 expressions are exactly of the form of this one. So now I can use this very nice formula in these expressions. Then we can bound. Let me first see this expression. This expecting value will be bounded by. Let me write just the bound. So here, the expected value of this expectation will be bounded by in the denominator. You will have the capacity of any point inside the well versus the meta point in the well, and now we need to compute the integral of this indicator, which is just the measure of the well. Yeah. So this is a bound for this expecting value. Let me see if I wrote it. So by using the formula, you get this bound. Now you need to estimate to get lower bounds for these capacities. And now let me talk something about these quantities Qn. So here you see that you have this product, and this product is equal to the sum. Okay, is equal to the sum, and let me write this sum in another way. You know that by using your your inner product with respect to the invariant measure, and your generator, you can recover the rates, or you can write the rates for your Markov process as okay. You just take the product of the indicator of this position, of this state, and L applied to the indicator of this other state. You take this product. So here you introduce one mu x there. So we need to divide by the mu of x. Okay, so this is very easy to verify that this is true. Yep. Then let me use that here. Here I need to. Here this subset means that you are summing the rates. You are summing all these rates. Yeah. So this expression Qn will be. You can write it like inner product of the indicator of x. L. Here I sum over the y's inside this subset. So you get the indicator of the subset EJ. Here you have your inner product. So this product is actually this inner product, and now you need to sum over x. Yep. And when you sum over x, inside the well I, then you just get the indicator of this subset, the product of this guy with this other guy. So this is, I think, a nicer way to write this expression of this sum. Yeah. Is it okay? Good. Now if I sum now over I, this product, I mean here, over J, I'm sorry. If you sum that over J, then you will get here the indicator of the complement of my well I. Okay, here I'm summing over all the J different of I. Okay, is okay? Well, okay, you have an n everywhere. You have n everywhere, actually, even in the stationary measure. Okay, so I'm saying that if you sum here over J all these values, obviously, if you sum over J, you will get an upper bound for just this term because all these terms are positive, and this expression is exactly the same thing as here, where this is an empty set. Okay, and so I can write this inner product as a capacity of the well versus everything else. Okay. So very nice. Now I by performing these calculations, I finally got this bound, this upper bound for this expected value. Okay. In which I have only capacities. Okay? So I'm trying to change my problem of estimating expecting times with estimating capacities. So far, I'm not assuming any irreversibility. Okay, these are just the capacities just as I have defined here. Good, and for the other expression, in the other expression, you will get the bound in the denominator. You will have the capacity again of x versus the meta point, and here you will put the expectation or the mean of this function, which is exactly this function, this number. So here, when you take the upper bound for this expectation, you will get the same upper bound that we had for this expression. Okay, so finally you will get the same bound, and this. So the only thing to do now to prove that these two limits are satisfied is to prove that this diffraction is going to 0. Yep. So in this way, it's okay. Any question? Okay. So in this way, first I have rewritten my QNs in this form by using this inner product with this something nicer, because now I can imagine some potential theory argument to prove that they are converging to something. So I think that this is nicer. And now, first you need to prove that this sequence of numbers are converging to something. When you have many wells, this is something that you cannot avoid. But if you have just one well, one jump, so this can be avoided. And now the only condition is that this expression is going to 0. Okay, so here we are requiring that the capacities inside the well must be very large compared with the interval capacities. Okay, very good. So now, thanks to this nice formula, we get, I think, an improvement of our last formula, our last theorem. Okay, and now one more ingredient is the trade process. We call that, in the case, for example, the case of the sticky orange process, you have some candidates of wells, but finally the union of these wells is not the whole state space, and you will see a delta set appearing in your model. Yep. Actually, in my example 2, do you remember where you have two arms? You are moving the balls. You see that if you start in the middle, the system is pushing you towards the middle. And so here, if you are thinking of reaching these endpoints, this is your well, and so this is also. Here you also have a kind of delta set appearing. Okay, so the delta set is not a rating. This is it's very frequent. You find the delta set. So how we deal with this delta set? I will introduce another thing here. So again, let eta be. I just need an irreducible Markov process. Okay, again with a generator L and with a unique stationary distribution mu. Now, in your state space, consider a subset. Now, suppose that you are interested in focus your rotation just inside this subset of the state space. suppose that your Markov process is starting somewhere inside this subset I, and then I will try to remove the times that my process eta is outside the subset A, and I will see what we obtain. So the trace of eta on the subset A is another process. Let me put here an ins, defined as a random time change of my original process. Okay, my purpose here is finally to get the following transformation of the Markov process eta. So this is your state space. You have fixed subset, not empty subset, of course. And now this is just a sample of your path for the process eta. Now these black times are the times that your process is outside the subset A. This is the red times in which the process is inside your set A. Now you just cut out these times, these black times. You remove these black times, and now you shift your other the rest of the path, so that now you have a path just inside the subset A. Okay, so formally what you do is first you define IT as the time that your process is inside the subset A. Yep, let me put an A here. And now this random time change is just the generalized inverse of this increasing function. This is the infima of the times so that this function A is strictly larger than S. Okay, this is also a standard thing. This is very standard in potential theory. Actually, you can change this indicator function by another function. What happens is that in the points in which this function is, the points in the state space, in your state space, in which this function is very large, your process is going very slowly, and the points in which he is very small, the process is very fast. So in this extreme case, you are putting a 1 inside the A, so here the speed of the process is the same, and outside A you are putting a 0, so the speed of the process is infinite. So you don't see the process when he is moving here. It's instantaneously that you are just getting the next step inside A. This is what happens. Actually, in our paper, we wrote the theory with H here in general, and we call it the H trace process. But it's not necessary here for our purpose. Okay, now, so this is the trace process I will use. Actually, you can try to prove this. For example, this nice formula. In this nice formula, it's enough to prove this formula for G equal to the indicator of a point, Y. So here you are just interested in three subsets, the point X, the point Y, and the subset A. Now you may you may concentrate your attention just in this subset of the state space, taking the trace of the process, and you can go on. Let me now. So in order to see that is useful, let me state some nice properties of the trace process. First, the trace is again Markov. Actually, since eta is irreducible, then this guy is also reducible. Is an irreducible. Okay. In the paper, we considered an countable set E, and then we proved that if, for example, eta is positive recurrent, this guy is also positive recurrent. Okay, so he is an irreducible Markov process, actually. So you still have the Markov property here. The stationary measure for this Markov process, trace Markov process, is essentially the same as eta, but you, of course, you need to condition your invariant measure, your stationary measure here over the subset A. Let me call it mu A. So this is, let me put an F here. This is just the original stationary measure. Mm-hmm. And actually, I can tell you something about the generator of this trace process. Please, I'm not assuming reversibility anywhere, okay? All that is true for any process without reversibility. I hate reversibility. This is the generator of the trace. You would like to apply this generator of the trace to some function defined on the set A. Okay. Let me tell you what is the value of the function in some point x. Of course, a point inside A. You can apply your original generator, but you need a function defined now over the whole state space in order to apply the generator L. So your F is just defined here inside the A, and the way in which you need to extend your function F must be harmonically. So let me put a hat here. Yeah. So this F is the unique harmonic extension of F over the whole state space. This is the original generator. Must be 0 on the remaining of the state space. Any question? It's okay? Yeah. So now, this is not too difficult to prove. Actually, the first thing that you can prove is that actually this operator, as I have defined here, is actually a Markov generator. This is just an exercise. It's very simple. Then maybe the difficult thing is to prove that the trace process has actually the Markov property. But if you use the Martingale problem, you can say, okay, let me take a test function on A. Here you have your your trace, and you would like to prove that this process is a martingale for your trace. If you do that, you are done. Yep. Okay? Here, this LA of F is equal to the original Markov process to this extension of F here, because the trace process is always inside the subset A, you can put here the extension of F. And now, again, your process is always inside, so okay. This extension is harmonic. So L applied to this function is equal to 0 outside A. Okay? So here I can forget the A. Can I forget the A? The time change, with the time change. I need to take the, yes, I need to, because your definition of the trace process is without a random time change. So you need to use a random time change here to pass from the trace process to the original process, yeah? Okay, let me skip it here, but I believe that we are not very far from the proof. So we need to charge here the time, and then we may use that this is actually you will get something that is actually the Dinky's martingale for the original Markov process. Okay. Okay. At least I believe that. And so in this way we can prove that this was not the proof in our paper. We did it by hand, but I believe that should work. And so in this way you prove that the trace process is just a Markov process, and now it's very easy to check that this is the invariant measure, the stationary measure for this LA. Okay, now. In metastability, when you have these delta sets, then yep. In addition to your wells, you have this set delta, and in this case, what you can first do is take the trace process of your original Markov process just on the union on the union. Let me put an S here. On the union of your wells. So it's here that you take your trace process in order to avoid this delta set. Now that you have your process just concentrated, you have focused your attention just on the wells, the union of the wells, you are in the previous problem, and then you can apply the last theorem. Yep. Okay, so when you apply your last theorem, what you will get is everything with an A, yeah? Because so this is the generator of the trace process, and here you have the invariant measure for the trace process. So here, that will be my A. Yes, but the nice thing is that, as I have it here, you can't apply just the original generator. Here, you just need to extend your function harmonically. And the invariant measure is just the original invariant, essentially the initial invariant measure. So you can here put just the same invariant measure. You can change this trace process by the original generator. And the cause here, the thing that you have to deal with is this extension of the indicators. Okay? Well, you still need to prove that this sequence of numbers is converging to something. And now, you should have I should have written here the capacity of the trace process. But again, by playing this game, by doing this thing again, you will be able to see that that in the inner product here in the trace process, you can extend this inner product to an inner product on the whole state space. You just need to extend all your functions harmonically. But this was just exactly our definition of capacities. Remember, we put an 1 over one set, 0 over the other set, and then we extended the functions harmonically. So, the capacity of the trace process will be exactly the same as the capacity of the whole Markov process, just with a factor, maybe a factor here, but that will be the same factor here and here. So the expression here doesn't change. Okay, that is very nice with capacities. This is the very nice interaction between capacities and the trace process. Everything here without reversibility. Okay, this is a forbidden word today. Yeah, and another thing. No, this is true. Because if you remember, these numbers is the sum of these numbers over j. So here you will sum over j, and this is exactly the expression of the capacity. You remember? Okay. Very good. That was very, very nice when we found out that we were very happy. And so, in this way, when you take the trace process, you are in the good direction because the same estimates, because you can try to perform the same estimates, not for the trace process, which is not very easy to find the transition rates for the trace process. That is very difficult, but this kind of quantities, the capacity will be the same. This is our miracle. So you can apply we have applied our theorem to the trace process. So this will be the x corresponding to the trace process. You get that this trace process, the x of the trace process converges to some Markov chain, Markov process. You obtain your rate. And now what about the delta set? Because we just disregarded this delta set. We would like to prove something like the time, irrespective of the starting point in the well, the time that you spend inside the delta set is going to 0. Yeah, this is what we would like to have. And so in our theorem, this is not very easy, but okay, you can read it in the article. That in order to say that this is happening, is enough to say that. Very, very nice. It's just, if you are able to compute the invariant measure, here I forgot the name here, the invariant measure of the delta set, and you see that the invariant measure, the stationary measure of the delta set is going to 0 when you compare it with the measure of the wells, with typically the measure of the wells are strictly positive. So you will get this dynamic result. So this is just a stationary result, stationary hypothesis. You will get that this just after having proved all these things, yeah. And you have also this convergence, and so you have this convergence. Okay, so this is the additional, the very little additional effort that you have to do in order to finally get some complete result about the original process. Now that you have that, remember that here you have cut out some times, and now you can put your times again because these times are converging to 0, and the square root topology is good enough to see that now that the path, including these times in the delta set, doesn't annoy. So you can obtain again the Markov, the convergence without cutting out your times in the delta set. All that is written in the paper. Okay, so yeah. So again, I didn't use reversibility until here. This is the result which is valid without reversibility. But in the case of reversibility, when your process is reversible, your sequence of processes are reversible, you can estimate your capacities by using the Dirichlet principle. Yep. So tomorrow I will show some examples in which, including the sticky sequence process, in which we can actually verify this condition. And if I have time, I'll tell you about the unique result that we have about non-reversibility, in which Claudio got also a variational mix, a minimax expression for the capacity in the non-reversible case, and he was very lucky because with that we could use that to prove the convergence of the zero-range process in the case of the totally asymmetric. But okay, so this is our last turn today, and tomorrow I will come back to my examples of the first lecture. Okay, thank you.